So this is an abstract that's called LN2 FRISGO, a software solution for artifact mitigation in fast, high-resolution fMRI. And this is basically a direct response to the new upgrade of the Terra X, this XA platform, which is all different. And the high-resolution fMRI community is not really happy. FRISGO is a term that we tried to introduce maybe last year or the year before. It stands for fuzzy ripple-free imaging with short-term gradient optimization. It's trying to account for these artifacts that we are getting a lot when we do high-resolution imaging at 7 Tesla with EPI. Maybe I first start by showing you the images and the figures that we're usually dealing with. So those are the kind of images I mean. We have all kind of problems at 7 Tesla API. We usually have these phase inconsistencies, which can come from just bad shimming, but it wouldn't be so bad if we wouldn't want to do a lot of grappa on top of that. Grappa makes us very sensitive to any kind of B0 problems. Then we have these fuzzy ripples that are coming from magneto-mechanical inductive mechanical interactions of the third order shims with the gradients, specifically because there can be current flowing through these filter blades and through Earth. So we have these oscillations of the gradient resulting in these blurry clouds that we often have in API. But then also we have these short-term eddy currents that are not corrected for with the Siemens eddy current compensation, which very often manifest themselves as these kind of edge ghosts. Usually, we would be able to account for some of them also with DPG, dual polarity grappa, but since the upgrade, this has been included in the Siemens product, which means that it no longer works or at least it doesn't work for high-resolution fMRI with competitive TSNR values. Also, if you buy your Terra X directly from the factory, it's not so trivial anymore to just unplug your third order shim, which we can do still, or kind of some of the centers can, but basically the reconstruction solutions and the hardware solutions to these artifacts are no longer really applicable. So we want to have a post-processing solution and basically a LN2 program that works directly on the Nifty data to account for these artifacts and turns these artifact-driven images into clean images. LN FRISGO, which is a LN2 program. And the LN2 program is supposed to work with all kind of popular ways of doing dual polarity acquisition. So as always, you can acquire your grappa reference lines with 2 polarities. Usually in IcePad, I just average them and to do the grappa calibration and not do different kernels like in DPG. But then if you want to have these dual polarity images as nifties or DICOMs after you scan, you can have a scheme where you are writing out your data with different polarities for the first couple TRs as opposed to the rest of the time series. Or you can have alternating TRs every other volume, or you alternate your read polarities for different runs, which are all implemented in the 3D API way of doing this. So those are the kind of data that LN FRISGO wants to work with. And then there are multiple algorithms on how you can make those corrections work. And one algorithm that we proposed previously would be to take a sliding window averaging. So basically, I'm switching my read polarity, and switching the read polarity means that we still have the same ghost because odd and even lines have different polarities, but now we flip them. So the ghost is exactly 180-degree flipped. So we have, as the ghost is additively or destructively interfering with the image, exactly opposite ghosts between odd and even volumes. So if we take averages of neighboring volumes, the ghost cancels out, whereas the image intensity does not. And this was very efficient. However, neuroscientists didn't like it because they were worried about temporal leakage, so temporal smoothing, and because you're basically combining 2 TRs to 1, even though you have the same samples, and they're not statistically completely independent anymore. So one of the approaches that LN2 FRISGO tries to deal with is to have the first volume in the different read polarity, compare the other ones, then you estimate your error field and apply this to the rest of the time series, which is kind of following the DPG approach, and with the difference that we can also capture higher spatial frequencies, and also assuming that the ghost is kind of constant for the entire run, which is sometimes not the case. So we also need approaches that can capture temporal differences of these ghosts and how they evolve over time, which is, for example, one approach also included in LN2 FRISGO over here, where we are estimating the artifact-free images as part of your slice time correction. So if you have alternating read polarities in your time series and you estimate what the signal would be right between those different TRs, for example, with higher order spline interpolation, as it is always done in slice time correction, the signal from the artifact would be completely cancelled out, whereas the signal from the brain would be maintained. You can also try different approaches. For example, something maybe in between, where you're not really able to correct for kind of TR-specific changes in your ghosting, but rather kind of ghosting in the temporal domain of your trials, where you have your alternating read polarities, get your errors from pairs of images, which still might result in signal leakage, in the sense that these error images might also contain transients of your signal between those different TRs from your true bold signal. So we want to low pass filter this time series, and then the low pass filter cutoff would be your trial duration. So you don't have any leakage within the trials, but still you correct for changes in the artifact as much as you can. And last but not least, you can also just flip your read polarity between different TRs and between different runs. And if you have the same timing, you can just average those and account for the artifact. And this is how it looks in LN2 FRISGO and the various options of the algorithms of how you want to apply this. So now that we have this implemented, we can test it. And we can test it, for example, here by looking at a whole brain 0.9mm protocol in 1.7 seconds. So we had to quite aggressive grappa of 16. So we have those artifacts, which also means that we don't have a lot of activity in a single run. We do the slice time correction approach, run-wise correction, and so on. And up here, you see the most relevant information, namely the time courses for a block design. So for example, for the slice time correction, you do see that the time course is relatively smooth, so we don't have this jaggedness between odd and even runs anymore. And also we do see that our edges, basically at the stop of the run, the signal still maintains this elbow and runs down very sharply. Similarly, when we are back to baseline in this undershoot period, we maintain our temporal resolution. This is not the case when we do this moving window averaging, which also does not have this jaggedness. However, you do see that the signal kind of goes down before the task has really stopped, which is a tiny effect, really tiny effect, but it's an effect that neuroscientists seem to care about, because at the end, the time course almost looks identical if you would have TRs of 5 seconds for that matter. And also, you do see that the artifact that we're dealing with, this jaggedness, is not really that bad to begin with. Like all of these time series look rather similar. You can see that for the run-wise approach, where you assume that the ghost is the same across runs, like in DPG, there is a residual kind of jaggedness happening. For the low-pass filtered error removal, this is reduced a bit, but there's still kind of higher temporal frequencies remaining. And now that we have this implemented, tested, and we kind of understand what it does, we can try to see how much we can push things. For example, in protocols that I currently care about, like, for example, fast whole brain imaging, and here 3mm in less than 100 millisecond TRs, which is very aggressive grappa. And therefore, we do have these artifacts. We can account for them and still get good activation maps in 2-minute tapping and checkerboard trials here. When you want to do layer fMRI, for example, with 0.9mm whole brain and grappa 16, you can get down to 1.7 seconds TR, specifically with the new gradient amplifiers. And get these, like those are the very data from the previous figure, but also showing that you can get activation maps with a single run here. If you really want to push this for very thin slabs and kind of to actually see the layers with the naked eyes in 0.35mm resolutions, it helps a bit. It's not, the artifacts are not so bad, but there are still these artifacts, and then you can start to see these laminar features and these diving veins. And that maybe Alessandro will talk about also in the next abstract. To make sure that those are diving veins or not, we also tested LN FRISGO on the Farouk-style protocol of whole brain 0.35mm multi-echo EPI images, which takes 6 minutes. And then we pumped this through Chiara's machine learning vessel segmentation to kind of see the vessels at the surface and how they're diving in. So we kind of want to prove that LN FRISGO also would work in practice, that you can then later have insights on how the brain kind of shows high resolution features. And that's it. Already 15 after, but if there are specific comments, I would love to hear them. And before we move on to the next presentation, maybe Alessandra.
Can I make a quick comment?
Yes.
So, you know, the jaggedness that you're seeing, do you think that can be some sort of a ringing, like vasodilation type of ringing? Have you thought about that? Like maybe that's not an artifact?
Yes. I think like Buxton has shown, right, when he gave coffee to his participant, that he had this undershoot ringing to some degree. I guess in the runwise calibration, which I have in there, which is basically taking 2 runs and then averaging them, I would see it there as well, which I do to some degree. It is suspicious that the kind of jumping up and down is exactly matching my TR off, like on off. And that kind of when I shift my TR by TR half, that this is completely gone. So that it's not only synchronized with my TR, but then also kind of the zero crossing of my sine wave is there. I guess this would be clearer if I would look at for example, if I would take a long rest period with a random onset time, right? Because now this ringing that you're describing, which might be V signal or something, that the only reason why I would see this in my task data would be that the task kind of synchronizes this ringing, that it's not there like in kind of resting state mouse optical imaging where I've seen this a lot. It's just kind of on top of everything. So if you average a lot of runs, then it disappears. So here it would need to be kind of synced to task, where there is literature, I think, from Martindale in John Mayhew's lab in Sheffield, where they showed that the V signal can be synchronized with the task. Yeah. So there would be ways to test this. I don't really suspect it here, but I could look into it.
Okay. Yeah. Thanks.